Hello again. I'm Nick Leifker, and welcome to Management 409, Operations Management. On the last video, I went over the steps involved with PERT CPM, how to take a set of tasks and the completion times for those tasks and a set of predecessors, and use them to give us a blueprint on how to manage a particular process. In other words, see how long a project takes, and to see which tasks need to be closely guarded, closely managed. Now, that said, this isn't the most intuitive way to view a project. This isn't the most intuitive way to visualize a project. So I'm just going to talk for a moment about what is known as a Gantt chart. Because usually when you are involved with a project, usually you will visualize it as a calendar, if you will. And that's what a Gantt chart does. A Gantt chart is simply another method of representing the times in which each task will be performed. So instead of representing it as a set of nodes, as a set of tasks on some map, it represents it as a calendar, as a block. So let's take a look at the project that we just went over. Again, 6 tasks, each with a different task length. And this just represents it as sort of a calendar. You see where it has week 0, 1, 2, 3, 4, and 5. Think of those as dates. Think of those as weeks. You might represent week 0 as the week of May 18th. You might represent week 1 as the week of May 25th. You might represent week 2 as the week of June 1st. So you have task A here, and that task A is expected to take 4 weeks. So it starts at the beginning and takes 4 weeks. So you put that 4-week block on the calendar. And then you have task B, which is expected to take 5 weeks. And so you represent those 5 weeks as a block on the calendar. Well, once A completes, then you can start task C. And so task C takes up weeks 4 through 7 on the calendar. It's decently useful. It's better for visualizing what happens when. That said, it is a little more difficult from a calculation perspective. But you will oftentimes see projects in business represented as a Gantt chart because it does provide the calendar. It does provide a better view of what happens when. Now, there is a problem with what we've done so far, and that is that we've worked under an assumption. The assumption is that we would know how long each task would take. That said, we usually don't, do we? Good way of thinking about it. If you were to ask someone how long a particular task would take, like say how long you expect to take to complete homework, you'd probably give me some rough estimate, as to how long it'd take. You'd probably give me some estimate if everything goes well. And you'd probably be able to give me some estimate if everything goes absolutely wrong. And that's usually how we view project or tasks within a project. We have an idea as to how long it'd take, an expected time. We have a time that we expect it to take if everything goes well, a minimum time. And we have a time that we expect it to take if everything goes poorly, a maximum time. Well, the beauty is that we can use this. We know how to use this. In fact, we have tools by which we can use this. And what we do is we adapt that expected time, minimum, and maximum time just a little bit so that we can use it within PERT CPM. And that's what we're going to talk about with this particular video. How do we calculate PERT CPM when there is uncertainty, when there is variation within the amount of time that a task takes? So, for each task, we take that minimum, expected, and maximum completion time, and we convert it. We come up with a mean task time for that task. We're also able to come up with a variance of the project completion time for that, or variance of the task time. So, mean and variance for each task. We can then use that mean and variance to come up with a mean and variance for the entire project. Not only that, but we could use it to figure out the probability of completing the project by a given deadline. And that is what is involved with PERT CPM with uncertainty. So let's take a slightly different example. We have a set of tasks here, except in this case, instead of having some project completion time, in this case we have these estimates, this minimum expected maximum time. Also, we have a set of preceding steps, predecessors, like we would normally find within PERT CPM. Well, what do? Well, the first thing that we need to do is we need to convert this minimum, expected, and maximum time for each task into a mean task time. So, we can find the mean and variance for each task. So we calculate the mean for each task, and that's just going to be minimum plus 4 times expected plus maximum, all divided by 6. So you take that minimum completion time, with the amount of time it takes if everything goes well. You take the maximum time, the amount of time it takes if everything goes poorly, and you then take the expected time, multiply that by 4, how much you actually expect it to take, and then you sum that up and divide it all by 6. So this is, if you will, a weighted average, because you take the minimum once, you take the maximum once, and you take the expected 4 times. And you find the average of that, the weighted average of that, with that expected taking up 4/6 of the weighted average. So that's our mean completion time. We can also find the variance of the task time. The variance of the task time is just take that maximum minus the minimum, you square that, and then you divide by 36. So from this, we can calculate the mean and the variance of each task. So, for task A, well, we have a minimum of 4, minimum of 1, expected of 4, maximum of 6. So to calculate the mean task time, that's just going to be 1 plus 4 times 4, which is 16, plus 6, divided by 6. So that's 1 plus 16 plus 6, which is 23, divided by 6. That is 3 and 5/6, or 3.83. Now for the variance is just going to be 6 minus 1, maximum minus minimum. You take that, that's 5. You square that, that's 25, divided by 36. Well, 25 divided by 36 is about 0.694. So we find the mean and the variance for each task. In the same way, task B. So we have a minimum completion time of 3, expected completion time of 5, maximum completion time of 7. So to calculate the mean task time there, well, 3 plus 4 times 5, which is 20, plus 7, all divided by 6, well, that's going to be 30 divided by 6, which is equal to 5. Now the variance, well, that's going to be 7 minus 3, which is 4. You square that, so that's 16, divided by 36. So 16 divided by 36 is 0.44. We find the mean and the variance for each of these tasks. Now, it's a debate as to whether or not you need to find the variance at this point. If you're working in Excel, you probably will, because you can use automated functions to determine which variances you actually need. But at this point, well, if you're doing it by hand, maybe you might want to wait to calculate the variance. Again, it all depends on what you're doing and how you're doing it. You don't need the variance quite yet. You'll need the variance after you've calculated what the critical path is, after you've determined what the critical path is. So, how do you determine what the critical path is? Well, you determine what the critical path is by taking those mean task times that you just calculated and using those in good old PERT CPM. So you draw out the project flow map, with arrows for between predecessors and successors. You go forward through the project flow map to determine earliest start and earliest finish. And you go backward through the project flow map to determine latest finish, latest start. From here, you can calculate slack, and you could also calculate the you could also calculate the critical path. Okay, and there is one typo here, but I'll get to that in a minute. So we do that. We calculate earliest start, earliest finish, calculate latest finish, latest start, calculate the slack, and the typo is the slack at task E there. That should be 0.83, not 0.87. And from here, we calculate the critical path. In other words, that set of tasks that's going to determine, well, that probably will determine, let me clarify that, how long the project is going to take. I say probably determine for reasons that I'll explain in just a minute. So we have this completion time. This is our mean completion time. So we expect this project to take 13 weeks on average. So we have our mean completion time for the project. Well, that's, if you will, the middle of the normal curve. In this case, we're going to want all the other details of the normal curve. So we have the mean. Now we need to find the standard deviation. Well, in this case, it's important to remember what determined that 13 weeks. What determined that 13 weeks, what determined the mean project completion time, was the tasks on the critical path. So, to find the standard deviation of the tasks on the critical path, first we need to find the project variance. And to find the project variance, we just sum up the variances along the critical path. And maybe we calculated this before, maybe not, but if not, well, we would do that at this time. So in this case, we'd calculate the variance of B, using maximum minus minimum and squaring that and then dividing by 36, plus the variance of C, and we'd calculate that by finding the maximum and the minimum completion time for task C, squaring that and dividing by 36, and so on and so forth. And so we'd take those variances of the tasks on the critical path and we'd sum those up. We'd add those up. Remember, variances do add like this. So the variance of B plus C plus F, that equals the variance of B plus the variance of C plus the variance of F. We can't do that with standard deviations, but that's why we work with variances, because we can use variances in this way. Now, it's important to note that this is not always the case. 99% of the time it will be the case, but not always. Reason why might take a minute to explain. Now, suppose we have a critical path, and that's represented by the black normal curve here. Clearly, it takes the longest of all of the possible paths. That's how it's designed. But suppose it doesn't have a very large variance, and by extension a very large standard deviation. Well, what can happen is that a non-critical path, and non-critical path almost by definition takes less time than the critical path, that if this non-critical path has a large variance, a much larger variance than the critical path, what can end up happening is that if this variance is so large, then the non-critical path may have a much broader normal curve, to the point where for a given deadline, it may be the non-critical path that has a greater probability of not being completed by that deadline. So sometimes, okay, not often, but sometimes, it's the non-critical path that can cause us to all of a sudden not be able to complete a project on time. So the critical path almost determines everything, but not always. So, going back to our example, to calculate the variance of the project completion time, you take the variances of the tasks on the critical path and you add those up. So you add up the variance for B and for C and for F, and you see that that's 0.44 plus 0.11 plus 0.11, that equals 0.66. So we've figured out the project variance. Well, to convert that to a standard deviation, just take the square root. So the standard deviation of the project completion time is the square root of 0.66, which is 0.82. Now the beauty of this is that we now have a mean and a standard deviation. We have a normal curve. And we know a lot about normal curves. And we're going to use that to proper effect in the next couple of minutes. See, in a lot of cases, what we're really concerned about is, can we get this project done on time? Usually there's some sort of deadline we have to meet. Well, suppose in this case we have a deadline of 14 weeks. How can we find the probability that we're going to complete the project on time? After all, there's uncertainty here, there's variation here. So there is a possibility we may not complete this on time. So the first thing we need to do is we need to find the z-value for completing the project. So what is a z-value? Well, a z-value is a measure of the distance away from the mean in a normal curve that a certain point is, in terms of the number of standard deviations away. So if I say that I have a z-value of 1.22, that means that I'm 1.22 standard deviations above the mean. If I have a z-value of negative 0.35, it means that I'm 0.35 standard deviations below the mean. So the z-value, it is a way of putting numbers with reference to where they are on the normal curve. So we find the z-value for this particular situation. The z-value is just going to be the deadline, that deadline we're most interested in, minus the mean, all of that divided by our standard deviation. Mean is the mean project completion time that we found thanks to PERT CPM, and the standard deviation is the project standard deviation that we just calculated. So in this case, the z-value is 14 minus 13 divided by 0.82. So deadline minus mean divided by standard deviation. And so that's 1.22. So this deadline that we're most interested in is 1.22 standard deviations above the mean. Well, that's nice and spiffy and all, but what does that mean? What can we do with it? Well, it just so happens that we know a lot about normal curves. We know an incredible amount about normal curves. And from this z-value, we can convert this to the probability that we will complete the project before that deadline. So, how do you use a standard normal table? Well, the first thing to remember is that you have the z-values on the tops and the sides, and you have the probabilities in the middle. So in this case, we're trying to convert a z-value to a probability. So we have a z-value of 1.22. So if you look at the standard normal table, you'll find that the whole number in tenths digit is written along the side, and a hundredths digit is written up top. So what you would do is you'd go to the row that has 1.2, which, that's whole number in tenths digit, and then you'd find the column that has 0.02, that's the hundredths digit. And you'd see where those converge. And that, at that point, that number written there, that will give us the probability that we will complete the project by a particular deadline, assuming that that deadline generates a z-value of 1.22. So in this case, well, we see that a z-value of 1.22 corresponds to a probability of about 0.889. Now I do want to point out one other thing because it's, incredibly useful for those who know something about Excel. There's a function that allows you to convert z-values to probability in Excel, and you'll probably be using this in your project. It's called normsdist, Normsdist. You'll likely be using this for the project management portion of the project. So we have our z-value of 1.22. We convert this to a probability of 0.889. So our probability of completing a project before 14 weeks is 88.9%, or 0.889. So, that is how we solve a problem with PERT CPM with uncertainty. We first convert that minimum expected maximum value to a mean task time. We then use that mean task time and good old PERT CPM to find our critical path and mean project completion time. We use the variances of the tasks along the critical path to find the standard deviation of the project completion time. And then we find where our deadline fits on that normal curve to find the probability of completing the project by the deadline.